All right, so today we're going to look at how to design an experiment. Now, I'm hoping that you've had a chance to look through the notes, but in case you haven't, this entire second section is going to be all about designing experiments. So we're going to look at two examples here and then one more example of specifically something set up for blocking. Now, this first example, we're given the situation where we're asked to set up an experiment to evaluate whether or not vitamins can help prevent recurrence of blocked arteries in patients who have had surgery to clear them as needed. They selected 204 patients were recruited and given folic acid, vitamin B12, vitamin B6, or no vitamins at all for 6 months. So A, design a completely randomized experiment. Okay, so in a randomized experiment, when it says randomized experiment, is referring specifically to random assignments, and we'll get to that here in a moment. Notice that we do not have a scenario in which we can randomly select the subjects for this experiment, right? They were recruited. They probably volunteered. It is pretty much against the law to randomly select somebody and give them any sort of medication. So it is likely not the case that they, randomly selected these people. These people were probably volunteered themselves for this test, right? So first of all, we start off with our 204 patients. So for our design, we say, okay, we have 204 patients, and we're going to go ahead and box them. Now, like we said before, in order for this to be a randomized experiment, we have to randomly assign these people to 4 different groups. We have 1, 2, 3, and 4, and we're going to randomly assign them to one of these 4 groups. Now, how you go about doing this is sort of up in the air. In this case, it doesn't particularly matter because we have the option to, it does not specify whether or not we have to have the same number of people in each group. You could put 204 slips of paper in a hat and shake the hat up until you get, and number them all 1, 2, 3, 4. So where there's 51 ones, 51 twos, 51 threes, 51 fours, and shake it up and have people draw out of a hat. That is a randomized way to do it. You could use a random number generator, randomly generating numbers 1 through 4 until you get everybody assigned to a group. It doesn't really matter in this case. Whatever method you pick is fine because it does not specify. Now, once we have them sorted into different groups, into the 4 different groups, we have to give them treatment, right? The treatment in this case is the type of vitamin that they are given. And there are 4 levels to this treatment. The first level is the folic acid. The second level is the B12. Third level is the B6. And the fourth one, they are not getting anything, so they are our control group, right? So we have the one treatment, that's the different vitamin they're giving, and there's 4 different levels to these treatments. So it's a little bit clearer. Now, if you've looked at the notes, then you know that there's one more thing that we must have in order for this to be a legitimate experiment. In order for this to be a legitimate experiment, what we must have is comparison of our results. Compare our results, then why did we do the experiment in the first place? The whole point of this was to test to see if there's a difference between each of these vitamins and how well they cleared blocked arteries post-surgery. So we must test that. We must look back and see what happened, right? Okay, so that's part A. This is a completely legitimate experimental design. This is something you'll be asked to do on your assignment that's due Saturday, right? So we have our subjects here. There's 204 of them. We randomly assigned them to 4 different groups with 4 different levels of our treatment, and then we're comparing the results. That is essentially how you would design an experiment in this case. Now, the reason the random assignment is so important, just in case you didn't check out the reasoning in the notes, it's super important that we get some sort of random assignment, because that is the best way to negate any sort of underlying variables that may be contributing to our results. And the reason that we would want to do that is because essentially we're looking for causality. We want to show a cause and effect relationship between whatever our treatment is and whatever our results are. And if we can randomly assign them to their groups, then we can negate a lot of the underlying variables that may be at play, right? Maybe, people, you negate people's diets because you have random people with random diets in each group. You negate the idea that there's, maybe exercise plays a part in this case. You negate that because a lot of the people who are going to be in each group, since there's so many of them and they're all randomly assigned, there's a random assortment of people within each group. So you can, show if, for example, the control group doesn't show very much change, but maybe the B12 shows a whole bunch of change, because there's a random smattering of every kind of person in both groups, then we can say, yes, we have evidence that B12 causes the blocked arteries to give way. And that's a really powerful thing that we can do. Now, the second part of this question says, an article has come out that says that the possible effects of estrogen might have on vitamin absorption. What can we do? Now, we've already used random assignment to sort of negate that, but if we already know for a fact that something might play an effect, then what we can do is something that we call blocking, right? So when you block an experiment, what you're doing is you say, okay, well, I already know that there is something that plays a part in messing with my results. So I'm just going to take care of that right at the beginning. So estrogen, commonly found in females, essentially, right? So what we can do is separate our 204 people at the beginning. It doesn't say how many males and females there are, and it doesn't really matter. So once we have them sorted into males and females, then we can randomly assign each subgroup, each block, if you will, into 4 different treatment groups within each block. So again, we have the folic acid groups, we have the B12 groups, we have the B6 groups, and we have the 2 control groups. And yes, you can have multiple control groups. So basically our experiment just doubled in size, right? Because we are essentially doing it twice, once for the males and once for the females. Now, with this situation, we want to, again, compare the results of the vitamins within the males. We want to compare the results of the vitamins within the females. Oops, that's not what I meant, right? Talking and writing at the same time is hard. And then we compare the results overall. Now, it is possible that maybe you didn't know that males and females have differing levels of the hormone estrogen. Males typically have less estrogen than females. That's something you may not know. You can still accommodate for this by just saying, okay, I'm going to have one subgroup with high estrogen, and then you can still carry out the experiment the same way. You just, instead of referring to as males and females, you have low and high estrogen. And that's completely acceptable. You can do the same experiment, carry it out the exact same way, you'd probably get exactly the same results. So this is an example of the same experiment up here, but we have blocked this experiment. We have separated it into 2 blocks of low and high estrogen groups so that we can get rid of the potential bias that would occur from having a disproportionate amount of high or low estrogen in one of our subgroups or one of our treatment groups. So that is an example of blocking and how it can be useful. All right, question 2. The head of the quality control department in a printing company would like to carry out an experiment to determine which of 3 different glues results and 2 different drying temperatures. That's a terrible typo. Which of 3 different glues and 2 different drying temperatures result in the greatest binding strength, right? This result there. So first, design a completely randomized experiment. Okay, so in this one, we have 2 different treatments, right? We have one treatment where it's the different glues, and we have one treatment where it's the different temperature levels, right? So the treatment of the different glues has 3 different levels. The treatment with the different drying temperatures has 2 different levels. So if we're going to design a completely randomized experiment, remember this is about a printing company, right? They print books. So what we do is we say, okay, a whole bunch of books. We're not going to say how many. It doesn't make us specify books, right? And we're going to randomly assign the books to receive one of 3 different glue types. We'll call them just 1, 2, and 3 for simplicity's sake, right? So we're going to randomly assign our books to one of 3 different glue types. We also have the temperatures, right? So each subgroup is going to have another level or we'll call it of random assignment that's going to assign it to receive either the high or the low temperature. We need to compare the results of the temperatures first, so we'll compare the results here, and then of course at the end we can compare the 3 different glue types. Now there's nothing that says you have to sort into the glue and then the temperature. You can reverse these if you want, assign books to receive high or low temperatures, and then randomly assign each temperature group to the glue. For me, it just made more sense in my mind to assign the glue first and then the temperature, just because I figured that would be the order in which you make a book, right? That's what I was thinking of. But if it makes more sense to you, or you would rather just assign them to 2 different groups and within each group have 3 different subgroups, that is completely acceptable. But notice, because we had 2 different treatments, we had to randomly assign twice, right? Once here and once here. Anytime you have a treatment, you have to randomly assign your subjects or your experimental units to that treatment group. Otherwise, you will not be able to show causality, right? You have to get rid of any bias that may be underlying. Otherwise, you will not be able to show whether or not there is a causal relationship. We want to be able to prove cause and effect, or at least show a lot of evidence, right? In statistics, we don't really prove things very often. So if we are able to randomly assign these, just like we saw up here, then we can say with a decent amount of confidence that there is a causal relationship between between the glue type and the temperature and how well it holds. Since we have 2 different treatments, then we're testing the validity of 2 different causes on an effect, right? So if glue 1 at the low temperature holds the best, and then glue 3 at the low or at the high temperature holds second best, then we can behave accordingly, right? And that's something that is very useful to us. I mean, it would be if we were running a glue company. Now, the wrinkle here says other factors thought to affect binding strength are the number of pages in the book and whether or not the book is being bound as a paperback or hardback. How would you redesign this experiment? Now, we've already taken up a whole bunch of space here in this experiment, so I'm not going to redraw the entire thing. We know what blocking is now, so one of the things we could do is we could say based on paperback and hardback books, right? So I can say I'm going to separate all my books into paperbacks and hardbacks and then go through this entire process just like we did up here when we separated into low and high estrogen. And that would take care of the paperback or hardback question. Now, we can do this again for the number of pages. We can, if we want, block large page numbers versus small page numbers, right? So maybe books with 150 or more and books with less than 150 pages, sort them. I don't read very often, so I don't know what constitutes a big or a small book. But another thing we can do if we don't want to block this is something that's relatively easy to control. We could, if we want, only use books that have relatively the same size or same number of pages. We can say, well, maybe I'm only going to use books with 200-ish pages. Now, that would help in determining which glue is effective for books with this specific number of pages. The trouble with that is if there is a difference in glue strength for big page numbers versus small page numbers, then we wouldn't be able to test that. So if we want to limit our books to a certain number of pages, and we can control for that, and we can figure out just which glue is stronger for a specific number of pages without having that affect our results. However, if we want to know overall for all of our books which glue would be best, then what we should do is we should block this experiment for large and small books. It just depends on what your goal is for this. And as long as you understand that, then you can behave accordingly, right? That's a very powerful thing that you can do. And that essentially is how you design experiments. All right, so the second thing I wanted to do today is just honestly 2 more of the same types of problems. They give you an example of how to block, or an experiment that they want you to set up, and they want you to accommodate for potential blocking. Since we just did 2 examples like that, I'm not going to do 2 more. You don't need me to do that. Instead, I'm going to look at number 3 and 4 because they are pretty quick and easy questions. So number 3 says, what are the 3 basic parts to well-designed experiments? One of those basic parts that you already know about, we referenced before, is we must have random assignments. We must have randomization, right? If we don't have that, we can't show any causality. The second thing, really the first thing, if we're being honest with ourselves, we need to have some sort of treatment in our experiment, right? We have to take our experimental units or our subjects, and we have to subject them to some sort of treatment that we're trying to test, right? We want to find the effect of a treatment in an experiment. If we don't have a treatment, we don't have an experiment. Second, of course, we have to have random assignment, like we suggested before. And then third, the third part is we must have control, right? We must have something to compare it to. So we have to have control of our treatments, right? We can't just treat it, subject all of them to the treatment and then go from there. We have to have some control group or some other group that we are in control of, either through a second treatment or through no treatment at all, that we can compare it at the end, right? So those are the 3 basic things. Now, number 4 says, why do we block some experiment and what statistical quantity does it reduce? So as we've seen, the reason we block some experiments is because sometimes we have underlying variables that can affect the outcomes of our experiment if we don't plan for them, right? Now, if we had an experiment where we didn't accommodate for one of those underlying variables, one of those confounding variables, then we would likely either overestimate or underestimate the effect of our treatment. And we know the terminology for that. That is called bias. So when we block experiment, it reduces bias. It reduces the effect of bias in our results. And that's a very powerful thing. So there you go. This is essentially the lesson that you were going to receive today if you had come to class, but you're not in class. Here you go. I hope this was helpful.